Okay, so in this problem, or in this type of example here, we're looking at a situation where we're lifting a fluid. That could be a situation where you have a pole, maybe it's a below ground pole, and you're pumping the water out, or you're pumping the water out of a tank. One of the things we have to do sometimes is uh, drain water out of our fish tank, and so we pump it up to a certain height, usually some height above the tank, which I'll just call here some height h. That we're pumping stuff up to some height h. And so the situation is we want to compute how much work is required. How much work is required to pump all of the fluid out of our tank. Right, so our tank's sitting here full, we want to pump it all out. Well, some of the fluid, like the stuff near the top, right, that doesn't have to go as far. Whereas fluid that's way down at the bottom here, right, that's going to take more work because it's got to be lifted further. So the first idea is we uh, take our solid that we're pumping volume out of, and we subdivide it up into a bunch of little pieces, right? So there are little bands here, and so on all the way through here, from point A to point B. And so we pick one of these, call it the ith interval. So since this is vertical, I'll do it as y sub I minus 1 to y sub I. And so in this example here, I'm looking at this region here. And what I look at here is this is going to have a height of delta yi. Right? And what we do is we say, well, it's not exactly a solid, but what we can do here is just think of this as some area for that, cross section. Basically, what we look at it here is the area here of the cross section. So what we're looking at here is the area of the cross section there. So then if you take that area times its width, that'll be roughly the volume. Roughly the volume. And then we have to figure out how much are we lifting it. Well, we're lifting this one from yi up to your height of h. So that will be a distance of h minus yi. So that's the distance we're going to have to work it out. Okay, and so now we need to bring in some ideas here. We want to compute work. Well, work, so we're going to compute the work for lifting this one sliver. So work is, of course, force times distance, right? Just force times distance. Okay. Force, remember, is your mass times acceleration, but in this case, acceleration is due to gravity. But mass, remember, is your density times the volume. So density, rho, times the volume. Remember, that's what mass is. The volume times the density. So we just need to figure out these quantities. First, we need to figure out the mass we're lifting. From that, we'll be able to figure out the force that's needed. And then we take force times distance because we already know the distance we're going to have to lift it is going to be h minus yi. So we start by working out the volume of this thing. And we can say, well, the volume is just approximately the area of the cross section times the width, the height. So in other words, we find a function for the area of the cross section times delta yi. Then if we multiply that thing by the density of the fluid, we will get the mass. That should actually be little m for mass, not big M. Little m. Mass is just going to be that area of the cross section times the height of the cross section times the density of our fluid. And finally, then, the force that we need will just be the mass times acceleration due to gravity. So we're going to have A of yi delta yi times rho g. Rho g. And so finally, now that we know the force and we already know the distance d that we're lifting it, we can put it all together to get the work for the ith subinterval. The work involved would be, I'm going to put that rho in g in front, times the area of the cross section, times the height we're lifting it, and putting the delta yi at the end, just rearranging things a little bit. So that now we can integrate and get the area of our, or the work done, not area, the work of lifting this fluid out of the container. So it'll be the integral between your limits, because we would add all of them up, take the limit, and it would transform to an integral. So the integral would be the integral from a to b of rho g times the area of the cross section, that function, times h minus y. And remember, delta yi becomes dy, as we let the limit go to infinity. So remember again, this here function, a of y, in this example is the cross-sectional area. The cross-sectional area. Okay? So let's now set about looking. We're going to look at an example or two where we're lifting the fluid from some container up to some particular height. And that could be a height that's above your solid, or it could just be we're pumping everything out. Like if we're dealing with an above ground pole, then we're pumping it out so we can get the water out. Okay. So let's see what we got here. Well, we're going to look at an example in a moment. Sorry, I might just said the wrong word there. So we're going to take a look in the next video at an example of doing this, but I want you to again see and follow how we're actually just using these different physics formulas and building on them to eventually we get a function for our formula for our force, and then we can get back and put that together with our distance lifted to get work. So again, this is for lifting a fluid up out of some container.